sorry, not yet. Grade book is time lag on that. Well, we already talked about gases in two other chapters. You know, the combined gas law, and ideal gas law. But we're going to talk about gases in this chapter, gas mixtures. We're also talking about liquids and solids.
I'm already in the syllabus.
That's where right now you would tend to open the college. That's why you're sitting on this.
So let's look at a gas mixture like air. If we look at the composition of air, what is it? Well, this is, nitrogen, oxygen, argon, carbon dioxide. That's a long spelling. I've never seen anybody spell like that. This is source. Carbon dioxide. Well, there are many different sources for the composition. But you look at Wikipedia, you can see 78% nitrogen, 21% oxygen, and about 1% argon, 0.04% carbon dioxide. And so we'll just round it. Rather than calling it 78%, we'll go with what? Like 80%. 80% is a little easier to remember. So we'll just consider air 80% nitrogen and 20% oxygen. Let's just do it that way. Or if you want to be more precise, more accurate, that's fine too. You know, 78, 21. But I'm just going to go 80, 20. And let's consider this. The other components we aren't going to worry about, but the other components will add up about 1%. And so let's say I have air here. This container of air is going to consist of
78%.
Well, we'll just go 80%. 80% nitrogen and 20% oxygen. That's the composition of air. This is dry air, you know, with no humidity. If you have humidity in the air, it's going to change the percentages a small amount. That would be a little lower. All right. And so does this mean that, let's say I had 100 grams of air. If I have 100 grams of air, does it mean I have 80 grams of nitrogen and 20 grams of oxygen? And that makes up 100 grams of air?
That makes sense.
It makes sense, and that's normally what we think, but
It's wrong.
it's wrong.
Wow. Is it that the molecules have different weights?
I'm sorry?
Is it like the weight difference?
Yeah, the weight difference, exactly. And normally when we're dealing with percentages, it's percent by mass, but these are not percent by mass. These are percent by mole or molecules. And so what that means is I shouldn't frame it in terms of mass. I should frame it in terms of moles or molecules. So it would be like this. If I had 100 moles of air, then I would have 80 moles of nitrogen and 20 moles of oxygen.
And then you get the molar mass.
And that would be correct. Yeah, we could get the molar mass of air this way too. It would be a weighted average. Or if I had 100 molecules of air, or 100 molecules, the mole is just like a counting unit, so 100 dozen molecules of air. I'd have 80 dozen molecules of nitrogen and 20 dozen molecules of O2. So if I had 100 moles of air molecules, I'd have 80 moles of nitrogen molecules and 20 moles of oxygen. Or 100 molecules, it would be 80 molecules of nitrogen and 20 molecules of oxygen. And so it's not a mass percent for air composition, it's a mole percent. And since the molecules weigh different amounts, they're going to give you different mass percentages. We can get the mass percent So for example, if we did the mass percent, nitrogen and oxygen weigh different amounts. Oxygen weighs a little bit more, and so it'd be slightly biased in oxygen. So rather than 21%, it'd be more like 22%, because they aren't that different. Oxygen is 32 grams per mole, nitrogen is 28 grams per mole.
Does like the air follow like the density rule? Like are the heavier elements gonna go on the bottom?
Yeah, air follows the density rules, except it's not, it's not noticeable at small elevation. So for example, in this room, you can't tell the difference. Like the bottom, you think the heavier stuff would sink to the bottom of this room and the lighter stuff would go to the ceiling. Well, all these molecules are extremely light, and so you can't tell the difference. The only way you can tell the difference is if you're at sea level versus like 20,000 feet. Then it's different, the composition. And so that's what they call in chemistry, they call that fractionation.
Yeah, when the air is thin.
Yeah. What you find is this: you can tell the difference between ozone at sea level. Ozone at sea level is produced by pollution versus ozone up in the atmosphere, which is produced by natural causes. The ozone up in the atmosphere, high up there, has a higher percentage of oxygen 16 than 17 and 18, whereas the ozone that's produced closer to sea level has a higher percentage of oxygen 17 and 18 than that. And so you could see the heavier ones sink as long as you're looking at a huge time or a huge distance, but over short distances you can't tell.
Would you be able to feel the difference, like in your lungs?
No, not really. No. I mean, can you? That's like asking, can you taste the difference between heavy water and light water? You can't taste the difference.
Did that go for spring water? I know there's a big difference in when I drink spring water and I drink tap water.
No, but they taste different.
Yeah.
But they're not like.
Yeah. Yeah, it's because of the two things that you can taste easily is the pH. If it's more basic or more acidic, it's easy to tell. Like bases give it a more smoother texture, and acids make it a little bit more sour.
Did they put that in the spring water?
I mean, they make it more. They adjust the pH in some of this. Some of them are naturally high pH. Like for example, that Fiji water I think is pretty high pH, or alkaline water. But I was looking at some. I saw an advertisement for some water that had like a pH of almost 10.
I've seen 9.6.
expensive.
9.6.
Those are
Yeah.
the 99-cent store.
Yeah, that's pretty high.
We have one at home.
You have one.
They installed it. I get
Oh, it's
high
okay,
pH.
so high pH. Yeah, a lot of people like the taste of that. And then the minerals, what minerals you have in there will change the flavor of the water considerably.
I noticed too in some of the water they have electrolytes in them. How important is that to drink that water with electrolytes?
You need electrolytes. We need electrolytes. And so it's important.
What is
But
that?
how important
Is that an element they put into the water?
No, electrolytes are salts, minerals that are dissolved in the water naturally. For example, when you go, let's say, this water here has been purified. This water has been purified by osmosis, and so it comes out very pure. And then they add calcium chloride and sodium bicarbonate for the taste. And so what they do is they remove those and then remove all the minerals and then add minerals to suit the taste of the water. That's it. All right, so well, we're going to look at our two more things, and talk about those now.
Is magnesium sulfate a compound?
Yeah. A compound is, we have two types, molecular and ionic. Magnesium sulfate would be an example of an ionic compound. Sulfates are all soluble,
Uh-huh.
except for silver, lead, mercury, calcium, strontium, barium. So magnesium sulfate should be soluble. So this would be considered a mineral or an electrolyte or a salt that dissolves in the water.
Do you have calories?
It doesn't have calories. You can digest it. All right, so that's the mole or molecule ratio, but we know something, and that is this. The number of moles is proportional or equal to the pressure times volume divided by RT. And so the number of moles is directly related to the pressure, directly proportional to pressure. And so what we could do is we could do this. Let's say I had 100 atmospheres of air. If I had 100 atmospheres of air, is this true? That 100 atmospheres of air would consist of 80 atmospheres of nitrogen and 20 atmospheres of oxygen. Is that true?
No, that's the same. That doesn't make sense.
It doesn't make sense? Well, yeah, it may or may not be true. This is always true.
Oh, you know what? That does actually make some sense because of the
Right.
If the 20 atmospheres of oxygen weren't in
Well, okay, if that's always true, let's say 80% of the molecules here are, or what? 80% of the molecules in here are N2. 20% of the molecules in here are O2. And so what causes pressure? What causes pressure? The collisions of the molecules with the walls. And so 80% of the molecules that are colliding with the walls are nitrogen, N2, and 20% of the molecules colliding with the wall are oxygen.
So 80% is giving off?
Yeah, so 80% of the pressure that's generated is generated by the nitrogen, and
That's 80 oxygen.
20% of the pressure is generated by
20.
oxygen. So we have a total of 100 atmospheres of pressure, and so 80% of that would be nitrogen and 20%. So this is true.
Is it always true?
It's not always true.
Would you have to have exact numbers, like exactly?
No, we don't have to have exact numbers. It's not always true because, and I'm going to talk about when it's not true in a minute. This is always true. This is true at what we call constant volume, and I'll talk about what constant volume means in a second. But it's true at constant volume. That is, as long as the volume doesn't change and the temperature, oops, I need temperature too. Constant volume and temperature. As long as the volume and the temperature don't change, then the volume divided by RT will be a constant. So N is equal to a constant times P. And so the pressure is directly proportional to the number of moles. Let's go to this. Let's say I had let's say I had 100 liters of air. If I have 100 liters of air, is this true? Would 100 liters of air consist of 80 liters of nitrogen and 20 liters of oxygen? Is that true?
No.
No?
Could be true.
That's the same.
No is correct. It's not true. But
Aren't there gases?
true is correct too because it could be true.
We have to test first.
Yeah. And in fact, this is true. But it's true because the number of moles is going to be directly proportional to pressure or can be directly proportional to the volume. as long as the pressure and the temperature are fixed. And so this is going to be true at constant temperature and pressure. And so let me just summarize this here.
You seen 100 liters of air is equivalent to 100 ATMs?
No. No, this is separate. These are two separate ways of visualizing it. The thing is, these both can't be simultaneously true. One has to be true or the other. And so let's look at air. If we look at the composition of air, it's 80% N2. The 80% N2 means 80 moles of N2 out of 100 moles of air. Okay, so this is the percent composition. This is what we call the mole fraction. The mole fraction tells us how many moles of each we have in there. And this is equal to 80 atmospheres over 100 atmospheres. 80 atmospheres of N2 over 100 atmospheres of air. This is called the pressure fraction. Which is equal to 80 liters of N2 over 100 liters of air. This is called the volume fraction. Okay, we could do the same thing with O2. You know, O2 is 20% O2, which is 20 out of 100 moles O2 moles of air.
Not gonna R. Just remains the same all the time.
I'm sorry?
R just remains the same all the time.
Yeah, R is always the same. R is 0.08206 with our units. 20 liters of O2 over 100 liters of air. I need to do atmospheres. Sorry, atmospheres over 100 atmospheres, and then 20 liters O2 over 100 liters. All right, so the mole percent and the mole fraction, these are always true. The pressure fraction is true at constant volume, and the volume fraction is true at constant pressure, but it can't be simultaneously constant volume and constant pressure. That doesn't work. It has to be one or the other. And so this is typically the way we visualize air. When we visualize it as a pressure fraction, this is called Dalton's, or Dalton's law. It's pressure fraction. When we visualize it in terms of a mole fraction, this is called Avogadro's law.
They're both at constant T, right?
Yeah, both of them are going to be constant T. And so we're going to take a look first at Dalton's. And so let's take a box of air. I'm going to change the numbers a little bit. Let's make this 100 liters of air, but the pressure I'm not going to make 100 atmospheres. The pressure I'm going to make 1.0 atmospheres. And so I have 100 liters of air at 1.0 atmospheres. This air consists of 80% nitrogen molecules and 20% oxygen molecules. So the first way we're going to visualize this mixture is Dalton's. Dalton's is going to be a constant volume. So this is Dalton's at constant volume. Okay, so I have N2 and so when we visualize this 100 liters of air, 1 atmosphere, then how many liters of N2 do I have?
80.
No. I mean, 80's not wrong, but if I go on this top branch, then the correct answer is, how many liters of N2 do I have? I have
Wait for what?
100 liters of N2. That's how many liters of N2 I have. And so I'm just going to put all the N2 in this 100 liter box. In other words, you know what? I'm just going to remove the O2. And so I'm going to take this 100 liters of air and then remove all the blue molecules, all the oxygens from this. So if I remove 20% of the molecules, which are the oxygen, then am I going to get as many collisions against the wall?
Pressure
No.
went down.
I'm going to get 20% fewer collisions because there are no blues colliding here. And so what's the pressure going to be that I'm going to generate? Yeah, 80, it's going to be 80%, it's going to be 0.8 atmosphere. I'm going to generate lower pressure because there are no blue molecules in there anymore. Where did the blue molecules go? Well, the blue molecules are going to go in a different box. Now, how big is the box? How many liters of oxygen do I have? 100. I'm going to have 100 liters of oxygen.
Why is it 100?
Just because to keep the ratio.
It's 100 because I'm visualizing it as a Dalton's mixture, and when I visualize it as a Dalton's mixture, all the gases are going to have the same volume.
Okay.
And so I'm going to have 100 liters of O2, but there's no nitrogen in here. And so when I look at the 100 liters of N2, it's only the nitrogen molecules colliding with the wall. When I look at the 100 liters of O2, I only have the O2s colliding with the wall, and I have a lot fewer of those. And so what's the pressure I'm going to generate here? 0.2 atmospheres.
Makes sense. That's easy.
And so this is Dalton's law proper. Dalton's law proper says if I take 0.8 atmospheres of N2 and add that to 0.2 atmospheres of O2, how many atmospheres of air will I get? Yeah, so 0.8 atmospheres of N2 plus 0.2 atmospheres of O2 gives us 1.0 atmospheres of air. And so the total pressure is equal to the pressure of the individual components. So for example, air, I'm just treating as two components here, nitrogen and oxygen. And so the pressure of the air is equal to the pressure of the nitrogen, component 1, and the pressure of the oxygen, component 2. This is called Dalton's law. Dalton's law works as long as the volume is fixed. And so what I'm going to do is I'm going to just take this 100 liters and then keep the nitrogen in there and then take the blue oxygens and put those in another 100 liter box. And so I have 100 liters of air, 100 liters of nitrogen, and 100 liters of oxygen. And so this is the weird thing here. If I take 100 liters of nitrogen and add that to 100 liters of oxygen, how many liters of air do I get? 100, yeah. And so what I do is I just take it and then just combine it into the same box, basically. So I end up with 100 plus 100 equals 100. That's what we mean by constant volume. Everything has the same volume. So that's one way of visualizing this mixture. The other way of visualizing this mixture is as an Avogadro's mixture. So it's the exact same mixture, it's just a different way of thinking about it. And so for Avogadro's, we maintain a constant pressure. Constant pressure. And so what I'm going to do is I'm going to separate out the oxygen. If I separate out the oxygens, then the pressure's got to drop because there's no more oxygens colliding.
Like it's the volume.
Unless I squeeze down the volume. If I make the volume smaller, then I can generate the same pressure. Well, if I have 80% fewer molecules, then I better have 80%, yeah, this 80% of the original size, that is lose 20% of the volume. And so what I got to do is I got to make the container smaller in order to to have, okay, so I start off with 1.0 atmospheres of air. What I want to get is 1.0 atmospheres of nitrogen. If I get 1.0 atmospheres of nitrogen, then the box has to be smaller. Well, if the box originally was 100 liters, now the box better be 80 liters. Here. And then the oxygen. Yeah. I want the oxygen to also be 1 atmosphere. And so how much oxygen do I have? I have 1.0 atmospheres of oxygen. Well, if I have 1.0 atmospheres of oxygen, then the box has to be a lot smaller. Yeah, it's going to be 20% the size of the original. And so the box is going to go down to 20 liters in size. Does that make sense? And so what we have here is this. 80 liters of nitrogen plus 20 liters of oxygen gives us how many liters of air? 100 liters of air. But if I take 1.0 atmospheres of nitrogen plus 1.0 atmospheres of oxygen, how many atmospheres do I end up with? I don't end up with 2 atmospheres, I end up with 1 atmosphere. Why is that? Because I'm not crushing these into the same box. I'm just going to put the boxes side by side, and so the total volume will grow here. And so 1 atmosphere of nitrogen plus 1 atmosphere of oxygen yields 1 atmosphere of air. That's constant volume. And so Dalton's, we'll just write the equation for Dalton's here. Dalton's is P total is equal to the sum of the individual pressures, the partial pressures we call it. So it's the partial pressure of nitrogen, which is the pressure of nitrogen, plus the partial pressure of oxygen, plus however many gases you have in there. But the volume's strange. That is, the volume total is equal to the volume of the nitrogen, which is equal to the volume of the oxygen, which is equal to the volume of anything else in there. And so the volumes are all the same here. This is Dalton's. With Avogadro's, we have this situation. V total is equal to V1, that is the volume of the air is equal to the volume of the nitrogen plus the volume of the oxygen, plus whatever else is in there. But the strange thing happens with the pressure, that is the total pressure is equal to the pressure of the nitrogen, which is equal to the pressure of the oxygen. In other words, the pressure is constant. And so for Dalton's, the volume is constant. For Avogadro's, the pressure is constant, but they can't simultaneously be both together. All right, I'm going to stop here. I'll take a break and then start it.